Well, as things are loading up here, so we have a good framework in which to engage with fire to strategically plan it. And how can we build on that then to actually get at mechanical treatments in this example I'm going to show here, but we could also have prescribed burns or other management activity on the landscape to basically say, yeah, where are we going to actually implement treatments on the ground to make a landscape that's more resilient to fire, that increases or reduces the spread of fire across pod boundaries, hardens those boundaries. And to illustrate this, while we have the framework to help guide us, we also need tools and techniques that allow us to actually do this processing in near real time. Makes it so that we can incorporate lots of different information so we can compare and contrast and build off of all these different objectives. And so to illustrate this, I'm going to do a real-time demonstration with what's referred to as a notebook or a Jupyter notebook that can work on a desktop or in a web platform. So I guess this is a preempt to next month when Larry's going to be talking about some high performance computing options. And just to get started here, for those that aren't familiar with a Jupyter notebook, this is a web interface that allows people to write code and write up markup language so you can identify stuff. And we're going to zoom into Oregon for about 4 million acres, and we're going to run a series of scenarios to identify where we're going to actually do implementation on the ground to reduce the amount of the volume and fuels and harden pod boundaries. And then we're going to quantify costs and so forth. But to kick all this off, I'm just going to go ahead and run all the selected cells in here. I'm going to talk a little bit more about what this is actually doing. But we're going to step through each one of these cells, and a cell really represents an area where we're highlighting stuff. And so we can, in this context, I'm running this locally on my machine as we're talking, but we can also run this on a server. And in this case, we can download a whole bunch of data. What you see here is some code to do this. These can easily become buttons or dashboards. And I'm going to go ahead and minimize that. And the data that we're downloading is going to consist of an elevation model, a most likely class, whether it's non-forested pine or fir forests, basal area per hectare from remotely sensed imagery and field plots, the tonne on the landscape or tons of biomass, and the stem ton, so how much is actually in there with regards to volume that you actually might make boards out of, roads layers, stream layers, water bodies, a facility where we're going to convert the biomass into either chips or saw logs, or dimensional timber, and of course pods, because this is really driving our framework here, where we're trying to make resilient landscapes to fire and that harden those pod boundaries. And so here we can get a little bit more of a look at what the code looks like behind this, where we're running all those cells. And we can see that we're basically going to be importing a bunch of data, and then we're going to generate a map. And now, for those of you that aren't familiar with notebooks and coding, there's a whole bunch of Python code here. Well, here again, we can convert this into something like a button. And so we'll do that. And I'm just going to hide a bunch of that code, and I'll show it a little bit later on. But we can also use R code here. We can use Julian code, and we can use this exact same notebook on a high performance computing system or a local desktop, which I'm running right now. And at the end, I'll show you how we can do this in a high performance system. But we can generate nice little maps like this that demonstrate where all the roads are, what the elevation change is as we go from blue to white, as we go from low elevation to high elevation, our orange pod boundaries, and how those things, the juxtapositioning between all those different things. And so we can also use these to spatially define the desired future condition. In this case, we're going to frame it around those pods. We can use that desired future condition, and I'm going to go ahead and zoom in just a little bit so people can see as I'm going along here. We can use that desired future condition to define basal area thresholds and how much basal area would need to be removed to meet those thresholds. We can convert that into volume, so we can get an idea of how much is being removed off the landscape that has some sort of value to it, monetary value to it. At the same time, we can also quantify how much it costs to move that material off that landscape to the road segments, and then along the road segments to the sawmill. And because not every place where it doesn't meet the desired future condition actually is logistically capable of doing some sort of mechanical treatment, we can find potential treatment units based off of some other criteria. And then finally, we can calculate the costs and revenues, and we can visualize all this or summarize it at the pod level in this case, but we can use whatever boundary we want. And this is all based off of new tools that we've developed to do fast geoprocessing in parallel on desktop and high performance computing machines. So desired future condition, what in this context, what we're really talking about is we need to find places that we can actually operationally work within. So they're going to be areas that have forest or have this most likely class less than 1, which means it's non-forested areas. So we're finding pine and fir areas. We have to have slopes less than 50% so that we can actually do any sort of work on there with the machines. And we can say we're not going to be touching anything within an SMZ. Next, we can use those pod boundaries to and knowledge about what existing basal areas are required to reduce the spread of fire and reduce the flame lengths of fire. And so we can say right along the pod boundaries, we want to harden them. We're going to drop the basal area down to 15 square meters per hectare. But on north-facing slopes, we can allow a little bit more. It's wetter, so we're going to bring it down to 27 square feet per hectare. Or I'm sorry, meters squared per hectare. And on south-facing slopes, down to 20 meters squared per hectare. And we can visualize this. We can look at this from the perspective. We don't necessarily have to know where the trees are at this point. We can just say, hey, across the landscape, these are the rules, and we can lay them out and look at them visually. We can see that the blue areas represent those pod boundaries and being hardened. The red areas represent those south-facing slopes, and the green areas represent the north-facing slopes with the different criteria. And because those are raster surfaces with cell values, we can then calculate where we're depart from our desired future condition, and we can get it what's referred to as delta basal area per hectare by subtracting the existing condition here. And so what we're using is the remotely sensed data and the field data that we calculate basal area per hectares and trees per acre on the landscape, and we can subtract those two to get at where that is departing. Moreover, we can take that departure and calculate a percentage and translate that over into the total volume of saw logs versus the total volume of biomass through a series of nice little equations. And we can do this programmatically with our code, something like this with these new lines. And when we run those, we generate an output such as this, where we can see where the purple areas represented by 0, identify 0 volume being removed off that landscape or 0 tonnage. And the yellow areas represent high areas of volume that are being removed off that landscape. So now we get a good idea of how much we're going to actually be removing across the boards here. So how much does it cost to remove that value or remove that volume? Well, we can use another GIS exercise here, and we can do this in real time, and we can use machine rates where we quantify things like what's the dollar per hour rate to run a tractor trailer. In this case, we're going to put a number at 90. We're going to put a payload of 25.4 bone dry tons that a log truck can haul. We can do off-road costs at $80 per hour. These are all dynamic values. You can think of these as sliders or buttons that we can change these numbers. We can put capacity and payloads and speeds of what different skidding and or cable type systems can move material. And we can add in other costs such as harvesting and processing on a dollar per ton basis. Here again, we can run through some more mathematics. While we can quantify it as an equation, we can also implement it within a series of calls to a function here, where we can actually get at converting those on-road speeds to dollars per ton, and then converting those dollars per ton road segments into raster segments that now quantify the cost to move material along the roadway to a given facility. So we can see it gets more expensive. It becomes red as we move to the outside, and we bring that material to that facility versus lighter colors right around that facility. But we can also take it a step further and calculate the costs to move the material from the landscape to the roadway. And if we quantify it in such a manner where it's on a per unit basis, then we can combine those values to get at what the actual costs are, and what revenues are expected. And in this case, we can see there are some areas in which it's really expensive to actually do some sort of implementation. And so we can compare and contrast that in terms of making our plans. So how do we take that next step? Well, we know that we've defined departures from the desired future condition, but not all cells on a landscape really warrant implementing some sort of treatment. So we can put in other thresholds. We can basically say we want to find all those areas that have at least 3 tons per hectare, and that are within a 95% confidence interval, and that have at least 5 hectares in area and are contiguous. And so we can write a little bit of code to do just that. And we can process that code. And here we can see dynamically how those green areas represent those spots on that landscape, on that 4 million landscape. So now we're getting at something that's targeting down to something that's real, that we can actually calculate those costs. And since we know those locations, and since we know how big each cell is, and we know the amount on a per hectare basis, we can calculate the exact amounts, and we can quantify them based off of our pods. In the case that Kit had alluded to earlier, where we have a maintain, a protect, and a restore labeling for each one of those pods, we can see what the total tonne that will be removed off that landscape, how much that would cost, what are the expected revenues, and whether we see a positive or negative profit. Now that's an aggregate, because in aggregate, these values, generally we have profitable situations, but there are many cases in which that's not the case within a pod. And we're gonna zoom into that here in just a second and look just at that scenario where that doesn't, where there's individual regions that have negative values versus positive values. And as we can see here, it's still being processed. Here's the code behind this visualization component, and it should finish up here in a second. While that's crunching, I'm going to bounce over to where we can actually run this ourselves. Maybe we want to change some of those numbers. Maybe we want to look at it from a different perspective. And so we can go to a website such as this GitHub repository I've put together, and we can click on something like pods integration. And this is that exact same notebook that we just walked through, and you can open this up. Everybody can do this if they like, and I'll post this into the chat here in just a minute. And they can go into Colab, and now we're running on Google servers. I'm not running it locally. I'm going to be running it on Google servers. And you can basically come in here, and anybody that has a Google account can run this on their servers. We can run this on Cynet. We can run this on AWS, Azure, anywhere. And basically you come in here and you can run each one of the cells like I did before, or you can step through it individually. You can walk through and just click the run button here, and that'll actually get all the data here. It'll install everything on Google servers and run it for you. So let's see where we're at in terms of this processing. So what this process is doing right now, we've already calculated all the estimates, but we're doing the visualization component. And so I'm going to be loading in a whole suite of layers, including the outputs for the revenue and whatnot. And this is going to build a dynamic interactive map that we can actually use and work with. It should only take another few seconds here to run, and we'll actually get to see the overlay that's going on. Now, what's interesting about these tools, in addition to how quick they run, they also take full advantage of whatever your system has in terms of CPUs and memory. So if we step over to a high performance computing system, we can process the continental US quite quickly, dynamically. And in the output, we end up with a dynamic map, like you see here, that we can actually export out into an HTML. So we have some functionality here that we can look at. We can turn Esri street maps on in the back. We can turn layers on and off. We can look at it from a profit, a revenue, a cost, and a ton perspective. And we can zoom right down in and look exactly what's being shown here. So if we want to look at profits per se, we can turn those on. We can see where on the landscape we have some profitable being blue versus something that's almost a washout in terms of cost for implementation versus something that's redder in tone, like up here, that actually is expensive. And so now we can put this into the planning phase. And what we can overlay on this dynamic map is we can overlay pods or any other spatial layer, and we could play with this as if it's a WebGIS. For example, if instead of looking at pods, we want to look at fireshed project areas, we can lay those fireshed project areas on them. And what's becomes very apparent at this spatial scale is that these larger zones have a great deal of heterogeneity within them. What we're trying to capture with these project areas, with these project level planning tools, is to get past that heterogeneity and focus right in on where we actually want transition. So we can see that pods are designed specifically to address that containing of those fires and implementation on that landscape from a wildfire perspective. We can see that fireshed project areas are more generic in shape, and they don't necessarily capture that same framework or decision-making space. And then we can even zoom in further, and we can see that, well, not everywhere within the pod or everywhere within the fireshed has the same set of objectives in this context, or is it exactly where we need to reduce the fuel loads so that we can reduce flame lengths and harden pod boundaries. And so I'm going to go ahead and turn those fire sheds back off. And if we zoom out for just a moment here, we can see that a lot of the area that's identified within these pods that have most of the volume, so let's go ahead and turn volume on as opposed to profit. We have more volume being removed right along 400 meters of the pod boundary. So if we wanted to measure that, we can go out there and measure those distances, and we can see that, yeah, that's that 400 meters. That's a desired future condition we put in beforehand. And we can see that that's roughly what's defining why we're removing more material off the landscape right next to those pod boundaries. And those pod boundaries really correspond to something like, in this case, see, some of those trails along the roadway. So we can interact with this type of information quickly and easily. Moreover, we can summarize it to whatever planning unit we want, and we can look at all this tabular information that we've calculated and summarized for each individual pod. We don't have to aggregate to whether it's maintain, restore, or protect. We can look at individual pods, and we can display that however we want. And with that, I'm going to turn it over to Dave to finish up our talk here.
Yeah, thanks, John. I'm waiting for